In this video, I want to look at the properties of logarithms. Let's start by defining what those rules are. First rule we have is the product rule. It says if we take the log some base b of m times n, that is equal to log base b of m plus log base b of n. Notice how we started with a single log, and we've broken it apart using two different logs with addition between them. Next, we have our quotient rule. Quotient rule says if we take log with some base b of m divided by n, we can break that apart as log base b of m minus log base b of n. Very similar to the product rule, but instead of using addition now, we're using subtraction. But it's the same idea where we're taking that single log and we're breaking it apart as two different logs of just as single term items. And finally, we're going to look at the power rule for right now. It says log base b of m to the p power is equal to p times log base b of m. Here we're taking the exponent, we're writing it in front of the log so it's no longer an exponent, it's just being multiplied to that log. Now these rules might seem a little bit random, but let's see if we can make them make a little bit of sense. What we know about logs already is that logs are equal to exponents. The log just gives us the exponent. So if we think about rules of exponents, if we have an exponential expression like b to the m power, and we're to multiply it to b to the n, we can write that as a single term by writing it as b to the m plus n. Notice we're starting with two things being multiplied. We're starting with those two exponents being multiplied. We can break that apart as addition. It's the same idea as what we're doing with exponents. If we take two common bases with different exponents and divide them, we can write it as one exponential, but with the exponents being subtracted. Exactly what we see here. So logs give us exponents. We're taking those exponents, we're dividing them. We can write that as the two different exponents being subtracted. Then finally, if we have a base raised to a power, and then we actually raise it to another power, we can simply write that as the two exponents being multiplied together. And that's what we see here. We're taking an exponential or an exponent where we have that power being raised to a power. We can take it and write it as a multiplication of the two powers. So these three rules, really nothing new. We're just applying it in the logarithms rather than in the exponentials. How are these going to help us? Well, they allow us to take more complex expressions inside logarithms and write them as very simple expressions. When we go from this left-hand side to the right-hand side, that is going to be what we call expanding the logarithm. It also allows us to take multiple logarithms and write them as one logarithm. That is called condensing the logarithm. Both are going to be useful. So let me just write that down. Expanding, if we go this way, we're condensing if we go this way. We're going to do both things in this video. We're going to work on both things. And both skills are useful. So to give you a little bit of an analogy maybe, and when we have just products of things, when we're multiplying together, say binomials, if we have something like x minus 3 times x minus 2, we can simplify that as x squared minus 5x plus 6. But then we could also take an expression like this, and then we could factor it as x minus 3 times x minus 2. So this is kind of the similar thing, what we're doing over here. Condensing is kind of like simplifying. It's putting it back together as that simple, just written out expression, not breaking it apart. Expanding, we're breaking that thing back apart. So again, when do we use these two things? Any number of places. Both are useful. If we're trying to solve an expression, we need to factor it. If we're trying to cancel out like terms, it might be easier to do so. Cancel out like factors. We need to factor that. If we want to combine like terms, that's when we might simplify the expression, or if we just want to see it written out in that simplified form. So both skills are useful. We are going to need to know how to both expand and condense. So let's do a little bit of practice with those skills. Let's start by expanding. Let's take as our first example log base 3 of 2x. Alright, so what I see I have here is I have the product of two things. The product I know I can take and write as two different logarithms using addition. So I have log. I have to keep the bases the same. That is key. The bases have to remain the same. Log base 3 of 2 plus log base 3 of x. A lot of times when we see a number sitting next to a variable, we get used to just reading that as 2x and thinking it's all attached. And it is attached, but it's attached through multiplication. So we have to remember we can take those expressions and break them apart using our product rule. Let's take another example. Let's take log base pi of 5 divided by y. Same as before. I want to expand it. I'm going to take this single log with two different things inside of it. It's this quotient of two things. Write it as two different logs. I'm going to have to use a quotient rule this time, so I'm going to subtract. So I'd have log base pi, because that was my base, log base pi of 5 minus log base pi of the y. Let's take one more simple one, and then we'll make them a little bit harder. Let's take log base 5 of 10 to the third. Well, we can write this as the exponent comes to the front using our power rule. Then we have our log. Our base was 5, that has to stay the same. And then we're taking the log of 10. So log base 5, 10 to the third becomes 3 times log base 5 of 10. Alright, let's start blending these rules because we don't have to view these rules in isolation. Let's say we have log base 2 of 7x over y. Well, here I have a product of two things and I have a quotient of a third. I see 1, 2, 3 unique factors. And so what that tells me is when I'm done, I need to have 3 unique logs, or I need to have these 3 logs broken apart. Let's start with the product up here. We had the product of 7 and x, so I'm going to have log base 2 of the 7. That was the first thing I had. The product tells me I have to add log base 2 of the x. But then we have this quotient with y, and the quotient rule tells me I have to subtract this log base 2 of y. So notice we have 1, 2, 3 logarithms. Also notice that my bases stayed the same in all cases. Let's make it even more complex. Let's say we have, let's switch to the natural log, the ln natural log, just to show us it works exactly the same. Remember, the natural log is just a log with a base of e. And let's take 5 squared a cubed over b to the 5th c to the 7th. Well, now we have a lot going on. We have a product in the top, we have a product in the bottom. We also have exponents on each of these things. So up to this point, they've been relatively simple. I've just done them in a single step. This one I'm going to break up into a couple steps. I need to break apart multiplication. I need to break apart division. I also need to pull exponents to the front. That's a lot to have to do in one step. So what I'm going to do is I'm going to start by breaking the things apart as multiplication and division. Why am I not going to pull the exponent to the front first? It doesn't have a common exponent. We'll see an example in a minute where we do have a common exponent. But here, we can't bring, say, the 2 to the front because 2 is not an exponent on a, 3 was an exponent on a. So let's break it apart into the different factors first. Alright, so we have the natural log. The first thing we had was the 5 squared. Next we have that a. So I'm going to have plus the natural log of a cubed to y plus because those two things were multiplied. Then we get to the b. The b was being divided. So I'm going to have minus the natural log of b to the 5th And then finally we get to the c. And the c always kind of throws people for the loop, not necessarily c, but the fact that I have two things in that denominator. So here is the common error that I see. A lot of people say, hey, that c is being multiplied to the b. I know with multiplication, it has to be a plus. But that is wrong. That is not true. We were not taking the c and multiplying it to all these expressions. We were only multiplying the c to the b. These were the only two things in the denominator. So there's two ways that I can deal with this. One is to put in parentheses. I was multiplying these two things, the 5 and the a. I was dividing by both the b and the c. So I would put minus, and the b and c being added together, but really subtracted because that negative sitting in front. You can do it like that, that is fine. Or the other thing you can do, or we could actually get rid of those parentheses and subtract off the natural log of c. Now, had I had those parentheses there, let me just go back and say we had them for a second. Had we had those parentheses there, what we could think about is distributing that negative to both terms. Or you can do it in just one step. I don't mind how you do it. But the key is, anytime that things are in the numerator, they've got to be positive logs, because we're multiplying those things together. Anytime we have things in the denominator, those have got to be negative logs, because they are being divided. The c, we are not dividing b by c. But that's not what we're saying. We always do math from left to right. We're taking this expression. We're multiplying it by the a. We're dividing by the b, and we're also dividing by the c. We are dividing the expression as a whole by the c, so it has to be a negative. Again, anytime things are in the numerator, they'll be positives. Anytime they're in the denominator, they will be negatives. I'm not done, though. I have broken apart all of my factors. I've broken apart the multiplication and division. But I still need to bring the exponents to the front. So we'll have 2 natural log of 5 plus 3 natural log of a minus 5 natural log of b minus 7 natural log of c. Just pulling all of those exponents to the front, and there I have it, I'm done. Let's take another example. Let's say we have log base 3 of x squared y cubed over 2z. That's a 2 in front and a z, the z is crossed. And that whole expression is raised to the 5th power. Alright, just a second ago we said we had to break apart the multiplication and the division first. We couldn't pull the exponents to the front because the exponents were all different. If we look at this problem, however, there is a common exponent. That exponent is 5. So what I can actually do at the start is pull that 5 to the front. Everything was being raised to the 5th power. So the first thing I've done is I've just pulled that exponent of 5 to the front. Now I still have 1, 2, 3, 4 factors. I have 2 things being multiplied, 2 things being divided. So I need to break that apart using my product and quotient rules. So we'd have 5 log base log 3 x squared plus 5 log base 3 of y cubed. I have to scroll over a little bit here. Let me just zoom out a little bit so it's a little easier to see everything. There we go. Minus 5 log base 3 of z minus 5 log base 3 of, let me do the 2 first, just keep it in order. 2 and then the z. So we have our x squared, we have our y cubed. Those are being multiplied there in the numerator, so they're both positives. The 2 and the z were both in the denominator, they're both minus. Notice every single log has the 5 in front because it had the 5 in front here. The 5 was common exponent, and then we've broken apart our 4 different factors. This next point, I'm going to pull the other exponents to the front. So the 2 comes to the front, and it does multiply. We are multiplying all these expressions together. So 2 times 5 gives me a 10. 10 log base 3 of x squared plus 15 log base 3 of y minus, the next two expressions did not have any exponent, so they're just going to stay as 5s. And so there we have it, just to clean that y up a little bit. There we go, y. There's our final answer. Alright, let's take this one next. This one looks to be a little bit more simple, but let's walk through it really carefully. Here we have log base 3 of 15x. And really, I need to keep that 15x in parentheses. Anytime we have multiple things in that log, as I've done in all the previous steps, I have them all in parentheses. I don't always do that in division, because division, there's not really a way you can view that any other way. But it's a good idea, anytime you have multiple things inside logs, keep them inside parentheses. Alright, so here, it looks like I just need to break apart the 15 and the x like we did before. That is one correct step. But the thing with any number is it's potentially factors of other numbers. It is potentially two or multiple other numbers being multiplied together. And 15 is. 15 is the product of 3 and 5. So, if I think about it as a product of 3 and 5, that means I could use another product rule. I could write this as log base 3 of 3 plus the log base 3 of 5 plus the log base 3 of x. Anytime you have numbers in your logs, always break them down into their simple factors. The ones I've chosen up to this point, I chose them to be prime numbers. So I had 2, I had 5, I had 7. They were prime numbers, we couldn't break them down any further. But 15 we could factor as 3 times 5. Now if we notice, log base 3 of 3, that's just 1. And so we can actually take this first expression and write it without its log, because we had those other log properties earlier in a previous video. And we know if we take the log with a base of a certain number of that same number, that is just equal to 1. So this would be as simple as we can go. Let's take another one. Let's take log base 5 25y cubed. I'm going to do the same thing as the last one. I'm going to break down that 25. At the same time, I'm going to break up the whole expression. So I'm going to just save myself a step here. So I know that 25 is really 5 times 5, or we could write that as 5 squared. The sorry, my pen stopped working there. Clean that up. That's a log base 5 of y cubed. So we've broken apart the 25 and the y cubed as our two different logarithms, both with base 5. At the same time, I've written 25 as 5 squared because I'm trying to factor it down. If I look at that first term, that's another one of our log properties from previous video. That is just equal to a 2. The 3 can multiply to the front, and so we're left with 2 plus 3 log base 5 of y. Let's take log base 7 of the square root of 21x squared y. Alright, so we have the square root on this one. That's a little different. We haven't worked with the square root before, but remember, square roots are just fractional exponents. We could write this just as easily as log base 7 of 21x squared y to the 1/2 power. Anytime you see a radical, that is just a fractional exponent, which means that you can bring it to the front. 1/2 log base 7, 21x squared y. Same way we brought, I think it was a 7 to the front or no, is a 5. In this previous example right here, we brought that 5 to the front. That radical is just an exponent we can bring to the front. Next, I'm going to break apart this log into the, we have 1, 2, 3 different factors, but really we have more. The 21 is the product of 3 and 7. So I'm going to write 1/2 log base 7 of 3 plus 1/2 log base 7 of 7 plus 1/2 log base 7 of x squared, and then finally plus 1/2 log base 7 of y. I'm going to simplify any logs that I can. So the 3, I can't simplify that, but the log base 7 of 7 I can. That's simply equal to 1/2. And I'm also going to bring forward any exponents. So the squared on the 2 comes forward. 2 times 1/2 is just going to give me 1, so we'll have log base 7 of x. And then finally we'll have the 1/2 log base 7 of y, which we can't do anything with. So this would be our final answer. So what are the keys I'm looking for when expanding? How do I know when I'm done? I do think this tends to be the harder direction in terms of knowing when we're done. We're on the lookout for multiple things. We want to make sure that we don't have but just a single factor inside each of these logs. We also want to make sure that we don't have any exponents on any of the numbers or the letters, the variables inside the logs. We don't want any radicals for the exact same reason. We don't want to have any non-prime numbers. And then finally, any logs where the base match the number that we're taking the log of, we want to simplify those. So let's take one last one. Let's take log base pi of pi times x plus 3 squared times the square root of y minus 1. I need to keep that all in parentheses. So here I see I have 1, 2, 3 terms. I'm going to have to break this up into 3 different logs. So we'll have log base pi of pi. Next we're going to have our plus log base pi of x plus 3 squared. And we'll have plus log base 3, log base pi of the square root of y minus 1. Now if you want to go ahead and write that y minus 1 as the y minus 1 to the 1/2, that's fine. I don't need to see that you're writing that fractional exponent first. I understand that a radical is just that fractional exponent. Log base pi of pi is equal to a 1. In the second case, the 2 can be pulled to the front. So we'd have 2 log base pi of x plus 3. And then we'd finally have 1/2 log base pi of y minus 1. And that is it. That is as far as we can go. Notice we did not have any properties when we started this lesson. We did not have any properties that allowed us to break apart addition or subtraction. So those just have to stay as they are. Also notice how I included both in parentheses. Even though the second one, if we just simply pull the 1/2 to the front, it doesn't look like there's parentheses around it. Those need to be there. If I drop those parentheses like I have here, what I'm saying is I have log base pi of y minus 1. Same way this one was not in a log. That minus 1 is no longer in a log, which is why it's very, very important you keep parentheses around everything inside the log. That's why earlier I said it's obvious because it's just a division. But with addition, subtraction, and multiplication, it's not obvious what's inside the log and what's not, so you need to keep it in parentheses. Alright, we've done many examples now where we've expanded. Next thing we want to do, or next thing I want to do, is I want to go the opposite direction. I want to condense, because I said going both directions is important. Going and breaking it apart into all the logs is expanding, putting it all back together is condensing. So let's condense the following logs. Take as our first example, log base 3 of x minus log base 3 of y. Just as with before, where we're keeping all those bases to be the same as the initial, we cannot condense things if they don't have the same base. So we've got to have the same base to be able to condense these expressions. When we condense these, we see subtraction between them, We know that subtraction corresponds to division of the two elements. So we had an x and a y, we're going to divide those. That is our answer. We're taking these two different logs, we're writing them together as a single log of just that element where we're blending the two elements from before. Let's take log base 2 of 5 plus log base 2 of c. Well, addition tells me that I need to be taking these two things and writing it as multiplication. And for one more simple example, let's take 3 log base 2 of, let's do 4. That's telling me to take the 4 and raise it to the third power, which we can simplify that one. That's log base 2 of 4 to the third is 64. Alright, and there we have it, just like that. Let's make these a little bit more challenging. Let's say we have 3 log base 5 of 2 plus 2 log base 5 of a minus 4 log base 5 of b. Alright, so we see addition, we see subtraction. We know that the addition, the 2 and the a will have to be multiplied together. The b in the last log, that will have to be divided because we have the minus. I cannot put those together yet because they have exponents on the front of them. I can't combine the 2 and the a until I've dealt with the 3 with it. We always know we have to work with the elements being multiplied together first. We can't do these, or we can't do the addition before we do multiplication. So I know that I can write that 3 as an exponent on the 2. I know that I can write the 2 as an exponent on the a, and the 4 as an exponent on the b. Once I've written them like I have here, then I can write them as a single log by taking the 2 cubed, which is 8, multiplying it by the a squared, and dividing by the b to the 4th. As we saw when we were expanding, anything with pluses, any positives were being multiplied together, they're going to end up in the numerator. Anything with a minus, that's being divided, that's going to end up in the denominator. Let's take 1/2 log 5 minus 3 log x plus 2 log y plus, let's do a minus just to give us a little bit of variety, minus 1/3 log z. Alright, we see that we have exponents in front, so the first thing I'm going to do is put them back as exponents. So we'd have 5 to the 1/2 power minus log base x, it's log base 10, log of x, and we know it's base 10 because there's nothing written there. But now the x is cubed because we're putting the exponent back on top. We'll have log base 10 of y to the second minus log z to the 1/3. Now before, when we were expanding logarithms, we had to write those radicals as fractional exponents so that we could pull them to the front. There is nothing more simple or less simple about leaving as an exponent as a fractional exponent versus writing it as the square root. So you do not need to write this as the square root of 5 and the third root of z. You can leave them as a fractional exponent. There's nothing better or worse about a fractional exponent over radical. So I'm going to write my answer in 2 different ways. We still need to condense the fact that we have multiple logs. By the time we're done, we can only have a single log. So the 5, we're taking that, we're dividing it by the x. So x is going to end up in the denominator. We're multiplying by the y. Here we want to be careful, like we were earlier, that we're not saying, hey, the y is being multiplied to the x. No, It's not how math works. We're doing just the chain of events. So we're taking 5, dividing by the x, multiplying the whole expression by the y, meaning it ends up in the numerator, and then dividing the whole expression by the z, which means it ends up in the denominator. Again, think about positives as in the numerator and negatives in the denominator. So this is one correct answer. This is perfectly fine. Another way that you could write this is the square root of x, the square root of 5, y squared, over x cubed, the third root of z. Either of these is fine, okay? You do not have to write those fractional exponents as radicals. You can leave them just as they were. Let's condense one more. Let's take log base 2 of x minus 3 log base 2 of y plus 3. Right, so we go to condense this and we say, all right, the 3 is definitely an exponent on the y. And I can condense the first two, it'd be log base 2 of x divided by y cubed. But then we hit this 3 and we have a problem. We say, hey, it's addition, I should be multiplying something. But I can't put it in that log because it did not have a log. There's no log on this, so I cannot condense this into the logarithm. For just this instant in time, it is stuck where it is. But I do want to fully condense it, meaning I do want to put it inside the log. But if I'm going to put it inside the log, this 3 must be in some way tied to a log as well. Well, remember, when we're expanding, we saw that sometimes when we had the log of a certain base, log base, call it b, and then that b was raised to a power, that simplified to just that power. So using our other properties of logs, I know that I can add, or not really add, multiply 3 times log base 2 of 2. This log base 2 of 2 is just equal to 1. Why did I choose base 2? Well, that's the one that I needed. That's the one that the other two expressions had. In order to condense, I need that all the terms to have that log base 2. Log base 2 of 2 is just 1. Now that 3 is an exponent on the 2, so I can write it as log base 2 of x over y cubed plus log base 2 of 2 cubed. 2 cubed is just 8. And because we're adding, that's telling me to multiply inside the log. So we'd have 8x over y cubed. Could I have multiplied by that log base 2 of 2 in the very first step? Sure, I could have. That would have been probably a little bit faster. But the key is, anytime you have just that single value number with no log hanging around, it's got to have the log if we want to condense it. It's got to have the same log. It can't be a different log. So we were just literally putting that log behind it, log of its own base, because that is just equal to a 1. So now we have the expression fully condensed. So as I mentioned earlier, it's much easier to, I think, condense or know when you're done when you're condensing, because what we should be on the lookout for is just to have that single logarithm. It should just be the one log with nothing outside of it. All that stuff is inside the log. There is one last property that I want to discuss. So let's start by motivating this. Let's say I wanted to evaluate or find the value of log base 2 of 3. Well, this would be a problem because in our calculator what we see is that we have log base 10, it's the log button, and we also have the natural log, which is log base e. I don't have any other base there. Well, this brings us to our change of base property. Change of base property says if we have log base b of m, we can write that using any new base that we want. Let me fix this equation first. There we go. As log base, that new base a, whatever we want it to be. Okay, a is whatever we want it to be. So log base a of m divided by log base a of b. So a is whatever new base we want. And so a lot of times the way I remember this is if you just kind of put a line through this log. This is a thick line. Let me zoom out a little bit so it's not as thick. But if I just put a line through that log, it's still not doing a great job. Let me make it bigger. Log base b of m. If I put a line through the middle of that log, the m is bigger. It's naturally falling more into the top. The b is smaller. It's falling naturally more into the bottom. So that's going to help you remember. And the last thing to do is just to remind yourself of the fact that you have to create that new base. So let's come back to this problem, log base 2 of 3. That's the thing I asked you to find just a second ago. Well, I don't have a base of 2 in the calculator, but I do have a base of 10. So if I'm going to change this so that my calculator can evaluate it for me, if I take log of 3 over log of 2, using the change of base property, these two things have to be the same. The a that I've chosen is 10. There is an a there, it's just 10, so we don't have to write it down because it's standard log. So now this is something we can put into the calculator. And when we do, we get approximately, because logs are not precise values, they are irrational, 1.58496, blah, 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 blah. The next thing would be a 2, but I'll round it there to 5 decimal places. Why did I choose a 10? Well, it was one thing that I could put into the calculator. Theoretically, this should be equal to the natural log of 3 over the natural log of 2, because I should be able to choose whatever new base I want. And e is a new base. The key is we have to be consistent. So if I choose a 10 here, I have to choose a 10 down here. So let's type in the natural log of 3 over the natural log of 2. When we type that in, we get approximately 1.58496. Does not matter what new base we choose, it's always going to give us that same answer. If we had wanted to, we could have created a base of pi. Log base pi of 3 over log base pi of 2. And that's going to give us the same answer if we had a calculator that could do different bases. I wouldn't choose this one because that's really just kind of a pain. It's not wrong. I'm crossing it off not because it's wrong, but just because it's a pain. It's much easier to convert things to have the base of 10 or e because it's nice, easy, standard, or natural log. So the change of base property will be very helpful moving forward too. So we've studied a number of laws and properties today, or rules and properties. Practices, the first 3 rules that we worked on, really does just take practice, really making sure that you're comfortable with all of them. This one, I think a little bit more simple, but still very important. What we're moving into next is solving logs and exponential expressions. We're going to rely on all of these rules, all of these properties that we worked on today to do that.